Hello there, welcome back. We are continuing on with kinematics in one dimension, and we have gotten to one of my favorite spots, which is graphing motion. So one of the things that's going to happen in physics a lot is we're going to look at the relationships between variables and we're going to plot them on a graph so that we can see visually what's happening. And a great way to practice that is with motion graphs. So the first thing I want you to think about is if we have an object in motion. Now it might be going at a constant speed or it might be accelerating. We've already seen some formulas that kind of help back or allow us to calculate that. But the way their motion looks when we plot it out on a graph is going to look different, and we'll understand how their motion is working based on those graphs. So the first thing to think about is, what if I was to plot a displacement versus time graph, or something that's sometimes called a position versus time graph? So if I plot a graph, and on the y-axis, I put my displacement or my change in position. And on the x-axis, I put time. Well, if I was to say, imagine I have a linear graph, maybe something like this, okay? There's a lot that we could figure out from this graph. But one thing we could figure out would be, for example, the slope. So if I want to find the slope of this graph, you'll recall that slope is the rise divided by the run. So slope is rise over run. Now, the thing is to recognize though is this slope has an actual meaning. It's actually telling us something about the motion of the object. And so the rise here, if I look at the rise, I recognize that the rise really tells me something about the change in position of the object. So the rise is really a displacement or a change in position. And the run, you can see the run here is telling me how much time has gone by. So the run is really a change in time. Now the thing to recognize there, that a change in position or a displacement over time, we saw before that is velocity. So the slope of a d versus t graph gives us the velocity. Now something to keep in mind, is this velocity or is it speed? Well, the difference between the velocity and the speed are simply that the speed tells you how fast, but not where you're going. And the velocity tells you both, how fast and where you're going. From this graph, I can tell that this object is moving, let's call it forward, because it's in the positive direction. The slope could be positive or negative, which means the velocity could be positive or negative. So the slope of this graph does show velocity and not just speed. We can tell how fast you're going based on how steep the slope is, but you can also tell which direction based on whether the slope is positive or negative. So another thing we can do is we can take a look at a velocity versus time graph and look at how does velocity change with time. If I have a velocity time graph, well then things are a little bit different. Velocity versus time. Suppose I have a velocity time graph, and in this case, this is, again, maybe this is a straight line kind of going up this way. Now I want to point out that these two graphs, this displacement graph and the velocity graph, those are showing two very different things. This first displacement graph here is showing an object with a constant slope, which means a constant velocity. Whereas this other graph is showing a velocity that starts at 0 and increases over time. To put it another way, this velocity graph is showing an object that is accelerating. So again, we can do the same thought process where what does the slope mean? Well, the slope is going to be my rise over my run. But what are the rise and run in each of these cases? So slope is rise over run. Well, the rise is going to tell me the change in velocity. And the run is, again, the change in time. Well, the change in velocity over time, that's an acceleration. So the slope of a v versus t graph tells me the acceleration. Now this next one here is a little bit weird. This is maybe something that you haven't explored before, but in addition to finding the slope of a graph, we can also find the area under the graph. So let me give you another example. Suppose I've got a velocity time graph, and this one looks something like this. Now right away you can notice a difference. Look at this first velocity time graph. Do you see how the velocity is changing? Well, a changing velocity with time means an acceleration. This velocity graph is staying flat, which means the velocity stays constant, which means the acceleration is 0. You might have also noticed that the slope of this flat line is 0, and we just said that the slope of the line is the acceleration. So with all that in mind, what would happen if I found the area? When I say the area, what we're talking about is we're talking about the area of the curve bounded by the curve itself and the x and y axes. So if I was to draw a line straight down to my x-axis and then find the area of that shape bounded by the curve, in this case a flat line, and it wouldn't matter if it was a increasing line or a curve, but I find the area between the curve and the axes, the x and y axes. Well, in this case here, you can see that if I want to find the area of a shape, well, area is just length times width in the case of a rectangle. 1/2 base times height for a triangle. But regardless, this side of my shape is really a velocity. And this side here is really a time. And if I multiply these two together, so this is length times width, which in this case is the same thing as velocity times time. Well, you might recognize that velocity times time, if you think back to an earlier lesson, velocity times time is the same thing as displacement. And again, this is a displacement because I can tell, for example, the displacement was positive because the area is above the x-axis and the velocity was positive the entire time. So we've got three things to remember. To recap, for a d versus t graph, the slope of that graph tells you the velocity. For a v versus t graph, the slope of that graph tells you the acceleration. And for a v versus t graph, the area beneath the curve tells you the displacement of the object. So we're going to practice, and one of the best ways to practice this skill, or to check your understanding, I should say, is to try sketching out these curves. Okay, so we'll get two examples here. In this first example, imagine this red car and this blue car having a race, okay? And the red car, car 1, travels at a constant velocity the entire time. So the red car here goes at a constant velocity. Now, what would that look like? You could imagine that as the car goes along, as it travels, imagine this car has a little leak in its engine oil. And so it's going to drop 1 drop of oil every second. What would that look like after the race has been done? I think it would kind of look like you'd have a drop of oil every second, which means you'd have an equal spacing of your drops of oil. As time goes on, there's a drop every second. Now compare that to car 2, the blue car. This car has a constant acceleration. So it starts at rest, it's not moving at all, but then gradually over time speeds up faster and faster. And let's imagine, for example, that in this scenario, the red car and the blue car tie the race. So the red car just goes the same constant velocity, and the blue car starts at rest but speeds up and just catches the red car. Well, what would the oil drops look like for the blue car? If it's not moving at first, then I'd have a lot of oil drops clustered close together because I'm barely moving at all. But then as time goes on, the drops would happen further and further apart because every second you speed up, which means every second you're covering more displacement than the last. So what I'd like you to do is consider these two situations here. And so this graph here is going to be the constant velocity graph. And this graph over here is going to be the constant acceleration graph. And I say graph, but I actually want you to plot multiple versions. So I want you to plot the position, velocity, and acceleration graphs for both of these. Now they're calling this x, but you can think of that as dx or displacement in the x direction. That's fine. So what will the displacement graph look like? What will the velocity graph look like? And what will the acceleration graph look like? And I can't stress this enough. I really think you should pause the video here and try these out. Just sketch out anything and then unpause and see what you get for an answer. Okay? And I know you always do that, and so you've definitely done that, and here we go. Here's the answer. If this red car is traveling at a constant velocity, that means every second it travels the same displacement. That means that this graph here, my displacement graph, is going to be a straight line. Every second that goes by, the displacement increases by the same amount. That's a linear relationship. It's direct. When I look at the velocity graph, consider that the velocity is constant and positive, just like the slope of this line is constant and positive. So my velocity graph would look like this. A constant positive velocity means the same velocity all the time. So I would be at some positive number and I would have a flat line going straight across. And last but not least, what about the acceleration? Well, if your velocity is constant, then you're not accelerating. Put another way, the slope of the v versus t graph is 0. It's a flat line. That's 0 slope, which means my acceleration will be 0 the entire time. Okay, so how does this compare to the constant acceleration? Now, thinking in mind is that these graphs have to look different. The motion, if you're accelerating, is going to look different than if you're moving at a constant velocity. If you're accelerating, if the car is going faster and faster every second, that means they're covering more displacement each second than they did the second before. Think of the oil drops. The gap in displacement is small, but it gets bigger and bigger and bigger. That's going to translate to a displacement graph that is a curve that curves upwards. Now, for you fancy math folks, you might recognize that curve. You might know what that is. That's a parabola, or a half a parabola, or a quadratic relationship. So it's curving upwards. As time goes on, it's increasing. We said that the slope of a displacement versus time graph is the velocity. Well, that means that if this is speeding up, the slope is constantly increasing. It's becoming a larger and larger slope. It's curving upwards. So what will the velocity graph look like? Well, in this case, the car starts at rest, which means initially the velocity has to be 0. And it keeps getting faster at a constant rate, which means my velocity is going to increase over time. Now, it's a constant acceleration, which means the slope of this line has to be constant. And that means it's a straight line. Now, last is the acceleration. Now, the acceleration is the slope of the velocity versus time graph. This car has a constant positive acceleration, which means I would have a constant positive value for my acceleration here. Okay, so that's good practice. Let's try another one. Now, in this case, we've got just one car. So simplify things a little bit. Now, this one car does the following, okay? It starts at rest, speeds up to a constant speed and cruises along for a while, and then stops, let's say, fairly suddenly. Not like immediately, but just like pretty quickly compared to how it started. So you can think about what would the oil drops look like for this car. At first, the car's at rest, and so you can imagine the oil drops are clustered close together. But because it speeds up, they end up spreading out. Now, eventually, you get to some speed where you just cruise at that constant speed, so the oil drops are evenly spaced. But then you stop quite suddenly, so now the oil drops are more close together. So what would this look like? Our displacement, velocity, and acceleration graphs. And again, I can't recommend this enough. Pause the video, try it out, try it in pencil. Good chance you're gonna get it wrong, that's okay. And then come back and see the answer. So let's think about this. We've got kind of 3 sections: the car speeding up, the car going at a constant velocity, and the car stopping. So the first part of that is going to look like this. It's going to be a curve that starts to curve upwards. The car is speeding up, which means my slope is increasing. And so the initial phase there is curving upwards. Eventually we reach a top speed and we stay at a constant velocity. So we would have a section of the graph which would be a straight line. But then we stop fairly suddenly. Now, stopping fairly suddenly means the graph needs to curve and come to flat. Now, there's a few things that students do here that are incorrect. I want you to just think about what's wrong with each one. I'm not going to give it away, but I want you to think about it. Sometimes students think it should curve upwards, go flat, and then come back down like that. And that's wrong. And I want you to think about, why is that wrong? What's wrong with that idea? A little more subtly, now, a little more subtly would be sometimes students think that it curves upwards and then goes flat and then curves downwards. And that's maybe less wrong if there's such a thing, but there's still something wrong with that. And so think about what's wrong with that picture compared to what's actually happening. Okay, so we've got our displacement graph. Now we need to do our velocity and acceleration graphs. It might be useful to think of these things as being in 3 segments. So I'm going to think about this as being the speeding up, the cruising, and then the slowing down phases of the motion. For my velocity graph, well, the velocity is increasing. And it's increasing at a constant rate, so my velocity goes up for the first phase. Next, the velocity stays constant, so I would have a flat section here where we're going at a constant velocity. And last, the car stops, and it stops fairly suddenly, so I drop down. You'll notice that the slope of the first section and the slope of the next section are not the same. And again, I'd encourage you to think about, why is that? Why is the negative slope here a bigger, steeper slope, and the slope over here maybe a more gentle, gradual slope? Last but not least, I've got my acceleration. And so the slope of this velocity graph is a constant positive number. And then we don't accelerate anymore. It's not that we're not moving, we're just not accelerating. So my acceleration drops down to 0 and carries on. And in the last section there, well, the car's actually slowing down and stopping. So now my acceleration is negative. And so we drop down to this point right here. Notice that the flat line I've drawn here in the first segment and then the flat line I've drawn here in the second segment, there's two differences. One's longer than the other, it lasts for more time, but also it has a greater negative value than the positive value, absolute value, I should say. So it's further down here than this is up there. And again, think about why those two things are, because they do matter. Okay, that is it for graphing motion.